Good morning, my dear students. In this lecture 3 of Module 4, I will discuss some important concepts used in dynamics. It's a very small video. In your syllabus for this topic, only concept is required. Okay, numerical problem. Normally, they won't ask numerical problem in this section, but you can do problems in the PDF file I attached previously. Okay, now we will go to some important concepts used in dynamics. The first is D'Alembert's principle. Okay, now according to second law of motion, we know the resultant force acting on a body is F is equal to ma. So resultant force is equal to ma. Now if you rearrange this equation, the F is equal to ma, if you rearrange, that is ma, if you take in the left side, you will get sigma F minus ma equal to 0. Okay, this minus ma you can write it like sigma F plus minus ma. Okay, so if you put that minus ma as another fictitious force which is called inertia force, okay, then the equation of motion become sigma F plus Fi equal to 0. Okay, where Fi is the inertia force, Fi is minus ma. Remember to put minus negative sign. Okay, now if you closely look at that equation, sigma F plus Fi equal to 0, it look like the equation we used in statics. Okay, where resultant force is equal to 0. Okay, it is not exactly the same equation used in statics, but it is similar to the equation in statics. In equation of statics, the right hand side of the equation will get a 0. Okay, so if you consider that inertia force as one of the fictitious force, then the dynamics problem become similar to the statics problem, right? So D'Alembert's principle states that this net force, which is sigma F, and the inertia force, which is minus ma, okay, keep the body in a fictitious equilibrium, not the equilibrium we use in statics, in a fictitious equilibrium, imaginary equilibrium. Okay, that equilibrium is called dynamic equilibrium. That is the concept of dynamic equilibrium. Okay, so it is not the actual equilibrium condition, it is a fictitious or imaginary equilibrium. Okay, so that is actually the D'Alembert's principle. So the D'Alembert's principle is the net force acting on a body, which is sigma F, and the inertia force Fi together keep the body in a state of fictitious equilibrium called the dynamic equilibrium. Okay, now the equation 1, if you look at the equation 1, the dynamics problem using D'Alembert's principle, a problem in dynamics can be converted into similar type of problem in statics. Okay, so we already done a few problems in kinetics, not in kinematics. We done a few problems in kinematics. The same problems can be solved using the D'Alembert's principle. Okay, while solving the problems of kinetics, we use resultant force is equal to ma. So if you are solving the same problem using D'Alembert's principle, you can put it like resultant force plus minus ma equal to 0. Okay, it is same methods you can use, but the only thing is you have to take inertia force in the left side and put negative sign. Okay, this is the same problem, you can use it solve using the D'Alembert's principle. Okay, so that is the first concept in dynamics. Now we will go to the next concept in used in dynamics, which is impulse momentum equation. Okay, impulse momentum equation. So what is momentum or linear momentum, normally represented by P? We already know what is linear momentum. We all studied in plus 2. Linear momentum is simply the product of mass and velocity. So linear momentum of a body is given by, it is a product of mass and velocity. And remember, linear momentum is a vector quantity, since velocity is a vector quantity. So it is a vector quantity and its unit is kilogram meter per second, right? That is about the linear momentum. Now what is impulse? Impulse of a force. Impulse is the product of force and time taken or time duration. So impulse of a force is given by F. I is equal to F into delta T. Impulse normally represented by I. So impulse is equal to F into delta T. So we normally use the concept of impulse when a force is acting for a very short duration of time, and the cases where the exact value of force is very difficult to determine or practically impossible to determine. In that case we will normally use impulse. Okay, so by hitting a ball by a batsman, and similar kind of problems we use in the concept of impulse. Now impulse is represented by I. It's again a vector quantity. Its unit is, you know, from the equation, Newton second or kilogram meter per second. Okay, impulse has the same unit of linear momentum. Okay, how this is coming I will discuss after discussing the impulse momentum equation. Okay, how this the same unit of linear momentum is coming for impulse. Okay, now impulse momentum equation. So according to second law we know F is equal to ma, or F is equal to derivative of momentum. This is the correct representation of second law. The force F is equal to d by dt of P, or dP by dt. Now this equation you can write it like delta P by delta T, right? dP means change in momentum, so this equation you can write it like delta P by delta T. No problem. So if you cross multiply this delta T, or if you take delta T on the LHS, we get F into delta T is equal to delta P. Now what is F into delta T? F into delta T is nothing but impulse. So impulse is actually equal to change in momentum, right? Delta P is the change in momentum. Change in momentum means final momentum minus initial momentum. So that is actually impulse momentum equation. So the impulse momentum equation is impulse of a force, which is F into delta T, equal to change in linear momentum of particle, or impulse of a force on a particle is change in linear momentum of a particle or a body, both are same. Okay, so that's why, see, left LHS we had impulse, and right side we had change in momentum. Change in momentum as a unit kilogram meter per second. Change in momentum also has the unit kilogram meter per second. That's why the impulse has the same unit as the momentum. Okay, so that equation 1 is the impulse momentum equation. So that's the concept of impulse momentum. Okay, you should remember the impulse momentum equation, F delta T equal to change in momentum. Okay, now we go to the next concept used in dynamics, which is work energy equation. Okay, so work done, we already know this concept of work done is simply the cross product, sorry, dot product, not the cross product, dot product. Work done by a force is F dot S. S is the displacement. Okay, so work done is the dot product of force and displacement. Okay, so force is a vector quantity, displacement is a vector quantity, so work done definitely it is a scalar quantity. Okay, now work done is a scalar quantity and its unit is Newton meter or joule, right? Now energy, work energy equation, the next term is energy. Energy, what is energy? Energy is the capacity to do work. It is again is a scalar quantity. Its unit has same as that of work done, joule. Now kinetic energy, what is kinetic energy? Kinetic energy is a form of energy. Energy has different form: potential energy, kinetic energy, heat, a lot of forms of energies are there. So kinetic energy, what is kinetic energy? Kinetic energy is the energy possessed by virtue of its motion, or because of the motion of a body it has a kinetic energy. And the general equation of kinetic energy is half mv square. We already know this equation, half mv square, right? Now next thing is work energy equation. What is the relation between work and energy equation? What is work energy equation? So we'll start from the definition of work done, which is W is equal to F dot S. Now F you can replace with MA, right? Then this equation become MAS. I am neglecting this dot and vector representation. I am taking force and displacement same direction. There is no angle between them. Theta is 0. Then you know F dot S is Fs cos theta, right? A dot B is AB cos theta. Dot product of two vectors is AB cos theta. So I am taking the case where the force and displacement are in line, or the angle between the force and displacement is 0. So cos 0 is 1, so I can use Fs, right? So F I replace with MA and S simply S. Okay, so MA into S is the work done. Now we already know the equation, so I am putting this equation as 1. We already has the equation of motion, which is kinematic equation v square equal to u square plus 2as. From that equation, if you rearrange that equation v square equal to u square plus 2as, we will get v square minus u square by 2a as s, right? We will get s as v square minus u square all divided by 2a. Now I am substituting this value, this expression of s in equation 1. If I substitute s in equation 1, what we will get? W equal to ma into v square minus u square all divided by 2a. This a get cancelled, right? Then after cancelling a, I will get m into v square minus u square all divided by 2. Now if I am rearranging this equation, I will get w equal to half m v square minus half m u square. Now what is half mv square? V is the final velocity, u is the initial velocity. So half mv square is the final kinetic energy and half mv square u square is the initial kinetic energy. So the work done by a force is equal to final kinetic energy minus initial kinetic energy, or you can say the change in kinetic energy, right? Change in any quantity is final of that quantity minus initial value of that quantity, right? So that equation, which is work done by a force on a body, is change in kinetic energy of the body. So that expression or that equation is called work energy equation. So the equation 2 is called work energy equation. Okay, so that's all about this video lecture. Now in these three concepts are very important, and normally they will ask for 2 mark or 3 mark questions in university, and normally they won't prefer numerical problems, because in the syllabus it is mentioned only concept is required, so they won't normally ask. But there is a chance of asking numerical problems in this section. So as the in the PDF or in the class note I given, there will be numerical problem from this section, so try to solve, which the problems in these sections are very simple compared to the problems we already discussed. So try to solve this numerical problem from this section. Okay, thank you.